Et à cause de ça, ma présentation qui était prévue pour demain après-midi est maintenant. Et merci de par les organisateurs qui a la possibilité de parler maintenant, et aussi de Yvonne qui est prête pour changer. But this is enough French now. I will start now to talk in English. And my question is a little bit the same like our last presentation. I want to change what are some limitations and invariants and restrictions of degrees of freedom in a system where we have high renewable energy systems. And of course, one of the reasons is, this is of course very interesting actually to study this in the German case, because we have a very strong increase of intermittent renewables. This is particularly wind and photovoltaics and some biomass. And you see as a result, even the demand, the overall gross electricity generation is a little bit declining. And so this is the block of the remaining power stations. There is also the nuclear, and we have the phase out of the nuclear. There's in 2011 significant reduction of nuclear. I did not continue, but of course this is definitively some change which take place, and now we have to understand, or we can study the situation where we have more and more intermittent renewable and less conventional power station, how such a system could work. This is a composition of the renewable electricity generation in Germany. This is the most recent 2012 numbers. You see this is biomass, this is photovoltaics and wind and hydro, and the rest I have skipped. As you see, the first new renewable was wind, then came biomass, and now we have a lot of photovoltaics. As a result, this is a very costly system. This is the billion euros. We have the effect of the liberalization of the German electricity market. We have a reduction of nearly 20% of expenditures, even though that the government has introduced an electricity tax, so which otherwise we would have somewhere here 30 billion euros. And since 2000, since the beginning of the century, we have a very strong increase of electricity expenditures, total expenditures, and this is of course partly due to the fossil fuel prices, partly due to the additional cost of renewable energy. And to understand this a little bit, that is the situation of 2012. We have a total electricity bill 65 billion euros. That's the number I've just showed you. And out of this 65 billion, there are about 14 billion, or about 21%, is additional cost of renewables. Of course, the renewables itself have a market value of 4.8. So for this market value 4.8, actually the German consumers, industry, households, etc., have to pay 14 billions on top. And you see that is the value of conventional power generation, distribution, sales, marketing, everything. And here this is the transmission, the grid cost. So you see this is very, very strong impact on the electricity market. And then we have here, this is the electricity tax I have mentioned. This also is an important cost element. So actually, what is the government in Germany doing? They see what are the costly technologies. This is the net support that is a fed-in tariff minus the market value of renewables. And you see there are two technologies now which are relatively cheap, and these are the intermittent technologies, the onshore wind and the photovoltaics. And the remaining technologies, which play some important role, they are more than double as somehow offshore wind, very expensive, biogas, very expensive, and if you transform biogas into biomethane, even more expensive. There's additional subsidies. And if you add all these indirect costs of developing these kind of technologies, you end up with these numbers. You see photovoltaic is relatively expensive because you need significant grid extension, etc. But still offshore wind is double as expensive today as photovoltaics or onshore wind. and in between there is biogas. That is the actual situation. Biogas looks good because we have here combined heat and power generation, so some of the costs are allocated at the heat segment, 20% if this is only biogas, 20 euros per megawatt, and this is 70 euros per megawatt hour if this is biomethane which is fed into the gas grid. So then you know that we have this famous Energiewende, the German energy concept 2050, and we have of course these greenhouse gases, and this is a long-term plan until 2050, and what for us is important, the renewable electricity share. So we have here renewable share in energy consumption and the renewable share in electricity generation, and you see here these are the numbers which we are looking at, a very strong increase of these shares. And of course here this was decided in September 2010. The government wanted to extend the range, the operation of nuclear, so all these targets are somehow, I call it the price for more nuclear. But then came Fukushima, and the government has withdrawn the extension of nuclear power. So we have now a phase out of nuclear power. And as a result, of course, this target of greenhouse gas emissions are still the same. So particularly 2020 and 2030. So these targets now are much more ambitious than anticipated in the year 2010. And therefore, I suppose that we will not reach this target, at least for 2020, because there are no ideas to increase, whereas I think we will get this combined heat and power electricity share, we get these tools, and here this yellow, I don't know whether we will reach these targets. Assumed renewable electricity share until 2050. If you want to have these shares, you have to split these shares to the different technologies, biogas, onshore wind, offshore wind, photovoltaic, other renewables. And here is the secured load of these technologies. And so that means if you have this kind of combination of technology, your peak load, which is secured, is reduced by 2%. 2% is the contribution, the load contribution of the renewables, and here in this case 6.8%. That already you see you need a lot of backup technology. Maybe that is demand side management, maybe this is storage, maybe this is backup power stations. So these numbers, of course, you can change. We have thought that this is a little bit reasonable. There's no, each technology is contributing into this growth of renewables, but the individual contribution is different. For example, photovoltaic, there will be some growth now, but in the future the share of photovoltaics in renewable will decline, but then the offshore wind will become a major player because of the future cost expectation. Yeah.
Just a definition. What is secured load?
That is if you have photovoltaics during the night, no photovoltaics, so secured low is 0. But if you have biomass, you can assume the capacity, 70% of this capacity can be used in peak load. So that means you have a reduction of the peak load. You will see, this is a very important variable for our model. I will just show you the model. Yeah.
For the photovoltaic, it's the same. Peak load is in the day.
No. The peak demand in Germany is in the night, in 5 to 8 p.m. in a winter evening. So there is no sun. That is in hours. So we take the data of Germany. So if you have in Egypt, maybe the people need air conditioning, then you have a contribution to peak load. Yeah, that is. So we have done a lot of calculations. A collaborator of mine, he checked these data, and so I think that is very reasonable. And the idea is you have offshore wind has a better contribution. Onshore wind is not so good. Of course, biogas is 100% because we assume that biogas will in future be used with gas storage tanks, so that particularly in emergency situation when we have peak demand, then there will be biogas. So that is the assumption behind this. So, which means biogas is somehow special in this table. We have the renewable share without biogas, because the others, you are depending onshore wind, offshore wind, photovoltaic and other renewables, which is mostly hydro, depend on weather conditions. So you cannot calculate, whereas biogas is in principle something which you can store, which could be used as a backup technology. So we therefore distinguish between biogas and biomethane, of course, and all others. And this is all others, the share of electricity. We need this. You will see just in a moment why this is an important issue for understanding what happens in the electricity system. Of course, we have just heard before that biogas is not such a good idea to have it in the electricity system, because there should be biogas maybe, but of course we have here assumed that this is some biogas in this market. Of course you can change, then that you have this contribution. These numbers will be much less. We will see what are the implications of that just in a moment. So, of course, then you have to say we have actually a large number of data here between 2010 and January 2010. This is the wind generation, and you have two cases. We have here virtually no capacity contribution during a winter day, so that means this could be an hour where it is the peak demand, so that means the contribution of wind energy is close to zero, that we have assumed 3%. And then we have another thing, gradient, 8,000 megawatt. And you see we have, in this situation, we had 27,000 megawatt installed capacity. So if you add more wind capacity, you make this scale. We only upscale that. Yeah, this is the idea how, and this we did for photovoltaics, and for offshore wind we have no data, but we have no real data, no production generation data. These are not yet valid. We have, of course, in Germany generation data, but these are not valid because these installations very often they don't produce and so on. So we need measurement. We use measurement data. So if we have good data, so we will continue with the good data in the future. But actually we don't have real data. These are real data. That is hourly. We are looking at the day ahead market, and which is 1 hour. Yeah. So, and that is the result. The first thing is the ordered load duration. That means we have here the situation in 2012. There is the peak load. The hour 1 is the highest demand, and then you see the hour in the year with the lowest demand is about 40 gigawatt. So that is the load curve in Germany, and actually we can of course modify this load curve. If there is no demand side management, probably if there is a reduction of demand, then this curve would move downward. So then we have the residual load. That means what is to be in these hours. We have already assumed how much renewable energy is there without biogas, and then we calculate another ordered load duration curve, and the difference between these two represents the political share, which for 2030 should be 50%, but of course this is not 50%, it is 50% minus the share of biogas. Because biogas we put here into the residual branch. Now that is the idea. That is, we need for the residual power stations, we need also we put there biogas. Biogas is like a coal-fired power station. You can shut on and shut off it if it is necessary. So, and then what you can see here, first you see here there is some capacity missing. So that means this curve from the renewables is not starting here at the top. It goes a little bit here. So we have a little discrepancy. So that means the contribution is not 100% of renewable. And then we have here excess production, and we have to think about what we should do. We can do in principle two things. One is of course shut down the installation if there is more electricity generated from renewables than necessary, but we can also do some different things. For example, transform this kind of energy into heat. If, for example, you have a district heating system, you can put Tauchsieder, something to produce from electricity, simple technology, hot water, and then you can save gas or other fossil fuels to produce the heat. So that is the best way. Why it is the best way? Look what is the problem. This could also be used for energy storage. But of course, if you have to invest into a capacity which you can at the maximum use maybe 1,500 hours per year, this is very, very uneconomic. So that there are two reasons where you want to for energy storage. One is you have the storage for other reasons. For example, a battery in a vehicle. You need a battery, otherwise you cannot drive electric car. So that means you don't need the battery for electricity reason, but for driving. In this case, you can use this battery perhaps to charge during this electricity. And the second is these simple devices where you can produce hot water. You have hot water tanks in a district heating system. There is, of course, storage of hot water. So you can put some of this, and the additional investment is very low. So that means this is a very, very good idea. And of course, that would mean you increase the overall demand of electricity by this. So the ordered load duration curve. Now, what are the remaining non-renewable power stations? Now we come into the situation. It would be completely stupid if there is a power station to shut them down only to save CO2. You should keep it. But of course, you don't run this thermal fossil longer beyond this line, because the renewable energy should have priority. But of course, we have these technologies. Of course, here you see the nuclear, it's a phase out of nuclear, 2022. After that, we have no nuclear, but we have a lot of lignite. We assume that the existing lignite power stations have a remaining, an overall operation years 55 years, hard coal 50 years, gas 40 years, others 40 years. This is a lot of different types. So that means that is the different technologies. And you see, we assume no additional build-up. Here in this figure, it shows the present capacity we have, plus those which are already under construction. Because if you are going to construct, you will not shut down. But nothing which is only on paper. This we have excluded here. So that means these power stations are still there. So that means you have a capacity, and you have a total adjusted capacity here, which assumes 15% of the capacity is not used because you need backup, etc. So that means 2030 we have 45% capacity. So that means here this capacity is there. Yeah, so much electricity we can generate. This area we can generate from a conventional power station in 2030. So that you see you need additional capacity. And exactly that is what we hear. We have here the conventional power stations. And of course, some of these power stations are the so-called base load. This base load is typically that technology which has the lowest marginal cost. At the present CO2 prices, this is lignite. And these lignite power stations have about 6,500 hours, operation hours. Plus, you cannot shut down at zero because you must still have them on stream for technical reasons, for regulation power, and also because you have maybe to start them up very, very fast. So that means, of course, no lignite power stations will run. There are always 1 or 2 months where they had in revision. So, but this means this is baseload power. Of course, seen from a CO2 point of view, this would be a very CO2 emission system. So if you want to change that, and that was my comment to that question you posed, the question how to reduce CO2 is the greenhouse gas price. If the emission right is more expensive, that gas power stations become the base load, then this lignite would become here. So here, the order here, according to which the dispatch of this power station takes place, depends on the variable cost or on the marginal cost. The cheapest one is this one, And then comes the next one. Actually, this is lignite, hard coal, and gas. But of course, with a high CO2 price, and my opinion of a CO2 is 70 euros per, because if the CO2 price increases, and if there would be the gas, will not be here, but here, you need more gas and less coal. What will be the consequence? The coal price will drop and the gas price will increase. So the CO2 price must compensate for that. And our assumption is, of course, some modeling behind, that we will have a CO2 price of at least 70, sustainable CO2 price of at least 70 euros per ton until this lignite power station would move here. And that would reduce the CO2 emissions. Yeah, so that is very important. Now we want to discuss the new builds. We have to build new power stations to fill this triangle. And of course, what we can see here, there is an expected annual operation of new plants. And you see this is a little bit more than 1,000 hours. We have the same problem as in our storage system. We have for new investments, strategically only very small number of hours. That has, if you want to build in such a system a new power station, this must be a power station where the investment costs are as low as possible. So this will not be a combined cycle gas turbine, it will probably be a simple cycle gas turbine because the investment costs are cheaper. So that is very important because you have to finance this investment within less than 1,500 hours. And this is a very challenging task. That is one of the issues which, and this is 2030, if you would continue, you will see a different kind of problems. So now economics again. We have understood already something which a future power, of course this we can do for every year, but of course I was asked to show you only the principle. We can, what we do, we have these figures of course also for 2040, 2050, so that is obviously not very complicated with different shares of renewables, etc., etc. There are a lot of simulations which you can do, but this is the principle how we do. Now, what must be the market price in order to finance investments which have to be only operating in 1 hour? So for this we have the ordered day ahead prices in 2012. That is our, we have an ordered price line. This is the hour with the highest price, and then comes the second highest price, etc. At the end we have some hours with negative prices. And so the average price, day ahead price in 2012 was 42.60 euros per megawatt hour. Now, what happens if you would have not had wind? We have a model, this data put into a model, and then we have assumed in the model there is no wind. So the result would have been that in that year, 2012, the average price would be 48.06. And if there would be no photovoltaics, the average price without wind and photovoltaic would be 51. That means 8.53 euros per megawatt hour more. That means we have taken out all these two renewables out of the system, and this effect, this 8.53, that is the so-called merit order effect of renewables. If you have this fed-in system, then the price goes down. And of course, if you want to invest in a new power station and you want to refinance this investment and the price goes down, that is not a very nice, this is the reason why in Germany it's discussed of whether we need maybe a capacity market and all, but you have in France the same kind of discussion. The reason is mainly because we have this drop in the price. The overall market price goes down because there is a mandatory fed-in. Everybody can produce, it gets its cost, so you forget, produce and forget. You put it in the system, but in the system there is a reaction, and the reaction is that the price goes down. So now we assume that we need a simple cycle gas turbine, and we have taken data and so on. I don't show you the details, but now the question, what should be the price duration curve in a situation when there is a gas turbine which should be 1,000 hours per year? So during 1,000 hours per year, the price must be at least the cost, the average production cost of this gas turbine. Otherwise, you cannot finance this gas turbine. Yeah, so that means this is the minimum price, and then the price drops here, and it follows this curve, which in 2012 would be 46. So that would mean if you average, you get a price of 52.50. That means that would be the average price of a market, the day-ahead market, in order to finance a gas turbine, which should be operating at least 1,000 hours. Of course, we have 42. We need 10 euros more. The price must be 10 euros higher. Then we could, the day-ahead price, the average day-ahead price, then there is a chance for gas turbines to be financed. Of course, if this gas turbine should not run 1,000 hours, but 2,000 hours, the price must be higher, the average price. The same calculus, at least 2,000 hours, there must be the minimum price which is necessary to finance the average cost of the gas turbine. After 2,000 hours, this gas turbine will not produce, and then the remaining merit order curve. Why this number is larger than this one?
Because of the gas.
Very good. If you need more hours gas turbine, then you need more gas, and this additional cost of the gas leads to the best is if you need the gas turbine only 500 hours, you need, of course, a very high price for 500 hours, more than 220 euros per megawatt hour, but only for 500 hours, and the average price is then 51.13. So this is interesting to understand the challenges of a system where you have large shares of renewable. This is not what you will discuss tomorrow. It's not a scenario with with 100% renewables. But it is a situation in which maybe at the end you end in the 100% renewable, but on the way to that point you have to solve these kind of problems. Now we have seen what means conventional power stations. And of course, it is for me very interesting, and it's also challenging for you if France or somebody wants to build a new nuclear power station, at the same time wind, a nuclear power station which runs 2,000 hours per year. I'm very interesting how this works. But of course it is a question. I have no solution yet. We don't want to build nuclear, so I don't think in the German market what we should do. But if you do the same model like in Germany, it is impossible to finance a new power station. It is only possible to finance a power station where the investment costs per unit are as cheap as possible. That is the conclusion what we have here.
That's without carbon price.
Yes, actually the carbon price in 2012 was 5 euros per or 10. So that means if the carbon price goes up, then you can do that with carbon price. We have also in our simulation model, we have also the carbon price, but it would be another presentation. What is the impact of the carbon price on this system? Yeah, that would be. But the next thing is, of course, now we have an idea how long is the operation hours of present power station and new built power stations. So that helps a lot. And of course, everything depends on the share of renewables, etc. And we also have an impact on the price. We see what is the price. So we understand a lot. But what must be there in order that new investments come? But we can do some more. We can do actually before in these figures we have the ordered residual load. But we can also disorder, we can take them as it is, and that is this curve. That is the residual curve, load curve in 2030. And you see here that is it is January 1st January into 70 hours after the 1st January 0. So of course what you have in January, that is holidays, so there is probably very often situations in which the residual load is negative. So we have this excess generation in there. Of course, if you have a storage, you can use this energy here, store it and use it here. So that is, of course, an option. If you have a hydro pumped storage, you can pump this electricity into some mountain bassin and use it here as a backup system. So, but then you see it is very, very funny. And of course, if you have into each individual plant, which you, in our merit order, you can say how many plants are below in the merit order, before in the merit. So we have here a plant, 20 gigawatt capacity is better, lower marginal cost, and now this is the next power station. That is yeah?
I'm sorry, is this marginal cost or variable cost?
Marginal cost.
Marginal?
Yeah, marginal cost. But of course, if you have a linear model, there is no much difference between marginal cost.
Yes,
that is not really.
Marginal might be the last plant to produce.
Yeah.
Variable cost is for one plant, the difference between fixed and variable.
Yeah. So, but this is actually not really an important issue for me in this. So that means if you are here, if you have a power station which has which is at the beginning of the merit, a conventional power station, which is at the beginning of the merit order curve, you see during the first 20 hours, 18 hours, it will not produce, but then it will produce continuously. The next power station will have maybe reduced here the production. And here in our case, we see here, this is no operation. We have this curve, of course, we must smooth it a little bit. So we have said no operator will start if it is only for 1 hour. So we will, this is a task which is our next PhD thesis, to understand this a little bit, how to improve this. So we have said, okay, there is here this is only 1 or 2 hours, so this is no operation. Then there is consecutive operation. Then there is no operation and consecutive operation. Yeah, so that is and if this curve moves up, that means we have much more. We have a power station which comes later in the merit order. You see, it will not operate in the first 60, 58 hours, and then there will be some hours in which this plant operates, etc. So with this technology, with this methodology, you can define for each power station a histogram of consecutive operation. How many? There is, of course, 5 within a year, 150 times. This power station will start operate only for less than 10, between 5 and 10 hours. This is a power station which stands at 25 gigawatt. That means there are 25 gigawatt capacity better in the merit order, which have that is the situation. So this is a very interesting figure, because it shows you a statistic, how long time you will, if you start the power, how long it will start. It is, for example, interesting if this maybe can be a combined heat and power station. What you are doing if you need the heat, and what you are doing if this has to run when there is no heat demand. So this is next station. And that is consecutive operation, and the same thing you can also calculate the consecutive standstill periods in 2030. You see here, again, there are maybe in some cases, three cases, this is of course 45 gigawatt, so there are more than 260 hours without operation. But the same plant is also a lot of time, 65 times per year, it runs between 5 to 10 hours. So you understand the operation profile of this backup system. And of course, this helps again to understand what has to be done. And the next thing what we are wanting to do is in this figure, we'll go back. Here we need some flexibility. And that is the next step what we want to do. We want to include the flexibility of the individual power stations. We want to create a data bank, and we are going to do that for each power station, thermal power station, significant power station, what is the gradient, what is the speed, and so we can maybe even understand better how this operation will take place. And also maybe we get this smoothing, this problem what we have here in the last figure, this smoothing problem here. we will understand this. That is what we want to find out at the end. This is the first approach. We want to know the power station, how much is the statistical, the histogram in a typical reference year, what is the distribution of standstill, and these are the standstill periods and the operation periods for each individual power station, for each position in the merit order, and of course for each share of renewables. So a lot of conclusions. I think that is what I wanted to tell you, and I'm looking forward to an interesting discussion.
Thank you very much.